Hello everyone, and welcome back to our class in Artificial Intelligence and Machine Learning in Finance. We are still in our discussion of multiple linear regression, and after having seen the definition of multiple linear regression and how it is estimated, we want to have a look at the question how to select the variables to use in our model. Now, this is slightly different to econometrics, where usually you have an economic theory that guides you which predictors to select. But here in the realm of statistical learning and machine learning, it is rather a question of which predictors can increase the validity and the fit of your model. And that is why we will actually select our variables without much theory, and rather on the question how much correlation we can see between the response and the predictors, and which predictors help us get an even better fit of our overall model. So we need to select the variables, and this is the process of determining which predictors are associated with the response and which we should include in our model, and which are the significant ones. We have several alternative approaches at our disposal. The first one is that we compare the fit of all models and calculate measures of the model's overall fit. You can use, for example, Archaicus information criterion, AIC, the Bayesian information criterion, or the adjusted R-squared of our models. But this would also mean, in a sense, a brute force approach where we estimate all possible models, and this will become infeasible quite quickly, as the number of different models for p predictors is 2 taken to the power of p. So if we only had 30 variables, 30 predictors, we would get close to 1 billion different models. So you will not be able to do this, especially when you have thousands of variables. So what we need to do is we need an automated and efficient procedure to select a subset of models, and go back here, and there are 3 classical approaches for variable selection. The first one is forward selection. You start with the null model, which only includes the intercept and no predictor at all. You estimate p simple linear regressions and then add to the null model the variable from the regression with the lowest RSS, and you continue adding variables in this manner until some stopping rule is fulfilled. So for example, you would start with an intercept and then maybe add x3, then you would add x1, and maybe your stopping rule is already fulfilled, so you will stop with just 2 predictors, and that's forward selection. Now in contrast, backward selection is the opposite. You start with a model that contains all potential p variables, and you remove the variable with the largest p-value, and then you go down and try to see which are the variables that are insignificant, and you continue removing variables in this manner again until some stopping rule is fulfilled. Mixed selection is a mixture of the two. You start with a null model. You estimate p simple linear regressions and add to the null model the variable from the regression with the lowest RSS, and then you remove variables that turn insignificant when new variables are added to the model because of correlations between the predictors. I've told you in the last video that you should be careful when including or actually excluding variables from a regression, because it might be that, for example, variable x1 is just picking up the correlation of x3 with the response rather than x1 in the response. So because of this spurious correlation between predictors, it might be that the coefficient estimates on your predictors are biased if you omit important variables. If you now include variables and suddenly another variable turns insignificant, then in mixed selection, you might want to consider removing that variable because other variables are picking up the same correlation. And then you continue adding and removing variables until, again, some stopping rule is fulfilled. So let's look at this in R. We are using the credit card data, and you see the summary statistics for those different variables. You see the ID, which is just the number of the observation going from 1 to 400. We have the different income, the credit card limit, the rating, the number of cards, the age of the customer, education, gender, student, married, ethnicity also, and balance, which is our response variable in all these regressions. So we start with a dummy variable for student. Are you a student or not? We use the credit data and we try to predict the balance of the credit card. And again, we use LM in our, which is the linear model, so the multiple regression. You can see here that the dummy variable for being a student is highly statistically significant. We have a t-value of 5.35. And yes, we should include this variable. You can also see that the adjusted R-squared for this simple linear regression is close to 7%. So 7%, around 7% of the total variance is explained by our model. Now let's do this with the credit card limit. And again, the t-value is much larger in this case. Again, however, this variable is statistically significant in our regression. We can also see that the multiple and adjusted, actually it doesn't make sense that it's called a multiple R-squared here, it's a simple linear regression. The R-squared is 75%, close to, and we can now see that credit card limit, seems to have much more explanatory power when it comes to the balance of the credit card. So we should, if we were to choose, we should include limit rather than student. If we can include just one more variable, again, we should also include student. And last but not least, the same for income. High t-value, statistically significant. You can see here we have 3 stars. We have a t-value of almost 10 and an R-squared of 21%. Should also include this in our regression. We now look at the AIC. You can see the archaic information criterion for these 3 models. And with the AIC, it should be viewed as lower numbers being better, and lower numbers signaling a better model fit. So actually the third one is with income. Oh no, actually the second one is the lowest AIC. And we can now see how a multiple linear regression would fare if we include all 3 variables. So let's do this. We estimate a linear model with balance as the response and income plus student plus limit. And all 3 variables remain statistically significant. And we can now see that just including these 3 variables gets us to an adjusted R-squared of almost 95%. And the archaic information criterion is also much lower than for the simple linear regressions. So we can see, yes, we should actually estimate a multiple linear regression with all 3 variables. And if we were now to include more variables, at some point, I guess, we would arrive at some variables that we can leave out. Okay, so now, how do we assess the overall model fit? We've already seen the adjusted R-squared. The idea here is that if you remember the R-squared from the simple linear regression, it's, as a matter of fact, by including more variables, the R-squared can only go up. So what we need to do is, in order to prevent overfitting, we need to punish our model for excessively using variables. And this is done in the so-called adjusted R-squared. As you can see, it's basically the R-squared, but it will decrease actually, and it will be punished for the inclusion of unnecessary predictors. So any variable, any predictor that is included that doesn't reduce or doesn't add to the model's fit will actually lower the adjusted R-squared. And this is why actually here it's important to see that the adjusted R-squared is pretty close to the multiple R-squared, so all variables are actually contributing to the model's overall fit, and this is the good thing. So as you can see from the adjusted R-squared, we should use this multiple model.